All right, it's 12 o'clock. It's Wednesday. It's time for the Iowa Learning Farms Conservation webinar. Welcome everyone to this week's webinar. We're back to our original uh, programming with a presentation, so I don't have to ask all the questions. And I'm really looking forward to this topic. I've had the great fortune to work at the Neal Smith National Wildlife Refuge for the first part of my career. And I remember when I started at Iowa State, Dr. Keith Schilling was doing work down there and had about a decade of data. And I thought, wow, that's amazing. They've gotten a decade of data. And here we are 20 some years later, and they've still been able to collect data down at the Neal Smith National Wildlife Refuge, and great support also from the USDA Agricultural Research Service. A shout out to now retired colleague that Keith and I worked with for years, Mark Tomer, that was instrumental in keeping some of the things going. But we have with us today Dr. Elliot Anderson and Dr. Keith Schilling from the University of Iowa. Dr. Schilling is the director of the Iowa Geological Survey, and Dr. Anderson is an assistant research scientist at the University of Iowa. And they're going to talk to us today about water quality improvements following Tallgrass Prairie Reconstruction, 30-year trends at the Neal Smith National Wildlife Refuge. They break the record for the longest title, but that's okay. As I was reading it, I'm like, I'm not sure how I'd cut it because all of those things are important, kind of the Tallgrass Prairie reconstruction, and that this was done at the Neal Smith National Wildlife Refuge. Now, nobody came to hear me, so I'm going to turn it over to Dr. Anderson and Dr. Schilling.
Well, thanks, Matt. It's our pleasure to be here. We're going to tag team the presentation. I've got a little bit at the beginning. I'm mostly here to support Elliot and his analysis and what he did, but any questions that go back to the origin of this project, I'm around to answer those questions. So let me kick it off, and then I'll turn it over to Elliot. As we're all aware, grasslands once dominated Midwestern landscapes. So tallgrass prairie has covered Iowa for thousands of years prior to the European settlement. And it's always been part of our landscape portfolio in this state. You know, we've since replaced a lot of grasslands with cropland, but grassland has always hold a potential as a conservation practice. Now, whether we call it tallgrass prairie restoration or cool season pastures or whatever, grasslands is always part of that, as should be part of our conservation landscape. And Neal Smith National Wildlife Refuge is probably the best example of large-scale restoration in an agricultural watershed. The reasons that this project was born 30 years ago, 1995, are interesting, and actually they apply so well to the conversations we're having today. Of course, we know that non-point source pollution continues to be a major impairment. There's a lot of programs out there. And I'm going to take one more step back. Like this text comes from a presentation from 30 years ago, okay? This still applies today. Improvements in water quality are difficult to measure. I think we're all aware of that. And historically, little to no monitoring was done. Improvements were mostly assumed or estimated using models. That was particularly true with sediment reductions. You just run a model, you show a reduction, and call to win. Neal Smith and the origin of this project was done essentially to actually answer this question on how much is possible with landscape restorations. In this case, an effort to restore and protect native ecosystems. Like we've highlighted, this is a project that was born 30 years ago in 1995 through early work by the Iowa Geological Survey, particularly Carol Thompson. She set up this project to be funded through an EPA National 319 grant to set up as Neal Smith National Wildlife Refuge was being developed. As again, I think we're almost all aware, large portions of that watershed have been restored or reconstructed from row crop, its agricultural legacy, back to native prairie by the Fish and Wildlife Service. It was an incredibly unique project, again, with amazing foresight that was set up. It was originally part of a paired watershed approach, with Walnut Creek being with the Refuge being the treatment watershed and Squaw Creek being the control. We established upstream and downstream monitoring sites that started back in 1995. So with that origin, there's been two series of efforts at a decadal scale to look back at this data. I handled the first 10 years at the Geological Survey. Mark Tomer with ARS handled the next 10, and the following 10 has been a little bit also led by ARS, with not much data analysis done in the last 10 years. With that, I'm going to turn it over to Elliot.
So one of the things that really set the stage for this recent work that we've conducted is many times we've been involved in conservation projects that have been located at a plot or at a field scale. And often when we install a conservation practice there, we're able to go in and really detect what water quality improvements have happened right away. And I'll even show a couple examples of that at Walnut Creek later on. But it's very rare that you get an opportunity like this to see what a big conservation practice, such as land use restoration, does at a watershed scale. Often these things just aren't installed at a wide enough scale to have any sort of tangible impact some of the bigger watersheds that we have here in Iowa. So this was really the starting point. We thought this gave us a very unique opportunity. And so with a little bit of background that Keith provided out of the way, so I'm just going to scoot up here so you guys can hear me a little bit better with Keith in the background. This is a snapshot of what the land use looks like in Walnut Creek today, over in this map that I've got on the right-hand side. I like this figure quite a bit because you can immediately look at it and notice that within the Neal Smith Wildlife Refuge in Walnut Creek, the land use is very different to what's happening in the surrounding area. I want to point out three specific locations on this slide in particular that were really instrumental to all of the monitoring that's been conducted and all of the analysis we did afterwards. So the first is this Walnut Creek Monitoring Site 1, which is located at the northern end of the basin. This is important because this is the monitoring gauge that captures the area in Walnut Creek where the prairie hasn't been installed. So it's got this smaller sub-watershed at the northern end that has largely remained in conventional cropland. You can see that with the brown and a little bit of the yellowish color that's shown in this watershed's land use area at the top. So we have continuous monitoring there. We have another monitoring site, which is at the downstream end of the basin. And so this is downstream of all of that land use change that Keith described. This captures all of that bright yellow area, which is showing where the prairie now is. And then just as important, what we often do in this case is we try to isolate the impact of the Neal Smith Wildlife Refuge on the middle part of the watershed specifically. And so for labeling purposes of this project, we've referred to that as the lower basin here. And all we're doing for that lower basin is we're taking the loads of the water volumes that have been measured at the monitoring site 2, and we're subtracting those that have been measured at the watershed monitoring site 1 from that lower amount. So by doing that simple little, mathematical manipulation, we're able to really identify what's going on specifically within this part of the basin, and this informed much of the work that we do. So this is the official snapshot of land use that we have in the watershed over these past couple of years. And just draw everyone's attention here to the crops and the prairie. And this really is getting at the numbers that are behind the setup that I just described. Crops and prairie land are the major players within the Neal Smith National Wildlife Refuge and the surrounding Walnut Creek watershed. There is a little bit of forest, a little bit of pasture, a little bit of developed area, but cropland, prairie, that's going to get you over 80 or 90% of the way there. Also on these bar plots, I've got the all of Iowa numbers shown as a bit of a reference, and just like to point out the prairie portion here. So there's absolutely no prairie land within the upstream part of the watershed. By the time you get to this lower basin, so again, that's the distinct part of the watershed containing the Neal Smith National Wildlife Refuge, we're at about 45%, and that's totally different from the typical Iowa scenario where we have less than 1% tallgrass prairie making up our landscape currently. So very different from what we see in Iowa, and also very different from the upstream and downstream portions of Walnut Creek. So as Keith had mentioned before, there's been an incredible long-term monitoring effort that's taken place along Walnut Creek, and really wanted to focus on three variables specifically for this study. So stream flow, that's measured at both of these sites, basically usually the equivalent of a USGS stream gauge. The National Laboratory for Agriculture and the Environment goes and collects high-resolution data sets there. It measures stream flow every 10 minutes, and so it gives us a really good opportunity to understand what's happening from a flow perspective, basically throughout these past 30 years. They also conduct substantial water quality sampling, and nitrate and sediment are the two parameters that they've measured most often throughout these past 30 years. We have really, really good data sets consisting of continuous grab sampling, so varies a little bit, but about every 2 weeks or so, the folks over at the ARS will go out and collect a grab sample for nitrate, and they'll do a similar thing for sediment. With this particular study, they're actually looking at suspended sediment concentration, or SSC for short. It's one of the most common parameters that people use to classify all the forms of suspended or particulate matter that exist within the water column at any given time. So this is the great 30-year background data set that we had to play with that Matt described at the beginning of the presentation. Once we had that data, had it all assembled and gathered and organized, we conducted a little modeling exercise here to basically help us go in and produce the most accurate records that we possibly could of historical water quality at both the upstream and downstream monitoring sites. And so we used a modeling framework called WRTDSK to do that. We need to do something a little more sophisticated than just linear interpolation or just adding up all of the existing points. And WRTDSK is an industry standard. It's been developed by the USGS and has shown really great application for sort of multi-decadal studies looking at nitrate or looking at sediment. And the plot over here on the right basically shows how it works in action. So the black points that we have here are the original nitrate concentrations that have been sampled at the downstream site. And this continuous black line represents the daily estimates of concentration that are derived from the WRTDSK model. So it's basically pulling together relationships between, in this case, nitrate, things like stream flow, season, temporal trends, and the actual water quality data that's been collected to produce the best estimate that we possibly can come up with using these data sets for what's happened over the past 30 years. Once we have that in hand, the next step was really to go in and try to aggregate these daily values that we've got at an annual scale. You have everything at an annual scale. You don't really have to worry about seasonality from that standpoint anymore. And it provides a very, very nice template for going in and looking at how things have changed, what the temporal trends have been over the past 30 years. So in this study, we actually looked at 3 different parameters, but are all somewhat related to the same sort of concept. So the first here is mean concentration. So anytime we're talking about that, all we're doing is taking each one of the estimated concentration values that we have in a given year and just taking the average of that. So this provides a nice way of summarizing what the general concentration was at a site in a given year. So fairly intuitive, fairly easy to understand. Another thing that we looked at are yields. So talking about yields, we have a load. So the load is developed by multiplying stream flow water volume by a concentration for any given period of time. Again, here we're working at the daily scale. You do that, and then for each year, you aggregate those values together, you get a load, and then you divide that load by the drainage area, so the tributary area going into each one of the sites. So it's a nice way of looking at loads, but accounting for the variability in drainage area, which can influence how much of any particular water quality parameter is passing through a point at any given time. And then finally, we have a value here that's called the flow weighted concentration. So all we're doing for this one is we're taking the load that existed within each given year and dividing it by the overall water volume. So it's a way of getting at what the concentration was when you adjust for the varying flow rates that we have within a given year or within year to year. So 3 different parameters, all very important. We also did another little mathematical equation here at the bottom, in which we wanted to focus on specifically what was happening from the lower basin. So the easiest, and I think in many cases, this is the easiest and most intuitive way to think about what's going on here. All you're doing with this is you're taking the lower basin values and dividing those by the overall watershed values. So those are the values that are produced at that downstream monitoring point. And so this is telling you the percentage of nitrate or the percentage of sediment that's coming from that lower part of the basin. So this is really key for, again, just trying to isolate what specifically is happening within the Neal Smith Wildlife Refuge. I should also mention that when you're doing an equation like this, you can't really do it for mean concentration specific. So you can only do it for volumes and loads, things that you can transfer upstream or downstream that represent some sort of tangible mass or volume. Because this lower basin here just refers to a specific subset of the watershed, you can't go in and determine a mean concentration for that because it doesn't have any direct monitoring tied to that point. So hopefully that's clear. That's all a little bit of a preamble to get in some of the actual results that we found when conducting the study. So I'll just start with stream flow. I've got some of these average annual stream flow volumes shown in the table here and also plotted on the right. And so this column here is highlighting what the average annual stream flow yield was across these 30-year periods. And even doing something as simple as this, you can already come up and identify the influence of the prairie and some interesting things that we think are going on here. So you just look at the very top part of the basin here. So this is that upstream monitoring site. We had a stream flow, an average annual yield of about 290 millimeters per year. At the lower monitoring site, so this is encompassing the entire basin, that dropped to 270 millimeters per year. And if you're just focusing on the lower basin, again, that's the Neal Smith wildlife portion of the basin, that's even lower, 264 millimeters per year. So even something as simple as that, it looks like the prairie is having an influence. You see lower normalized stream flow volumes at the lower end of Walnut Creek than we do at the upper end of that top stream, at the top monitoring location. Another way we can look at this and more of a time-based perspective is shown in this graph on the right. So this is that equation that I described previously. So this shows the percentage of the water volume that's coming from the lower part of the basin within each year from 1995 to 2024. So as we can see, there's a statistically significant decreasing monotonic trend here. So what this is telling us is back in 1995, when the Prairie installation was just getting going, a larger part of this basin's water volume originated from the Neal Smith wildlife section. Nowadays, that's dropped. And so where it used to be at something maybe around 65, maybe around 75%, today it's closer to 55 or 60. So you run this sort of analysis, and you can see that there is a statistically significant decrease with stream flow across this 30-year period. One other thing that we explored with regards to stream flow was looking at some of the dynamics that are on that you can identify from these continuous records. Classic thing that's been looked at a lot in Iowa that we examined here is this what's called the base flow index. And so we have a way of going in and disaggregating any continuous stream flow record, pulling out the runoff component, pulling off the base flow component. And the base flow index is just that base flow component divided by the overall stream flow in any given year. And so if you do that, you see it's another sort of hierarchy, and base flow index is consistently higher in the top portion of the basin, so the upstream monitoring site, than it is within the Walnut Creek, than it is in the lower portion of Walnut Creek where the refuge is located. And so it seems like the Prairie has actually resulted in a lower percentage of base flow that comprises the overall stream flow component. That's what this data is sort of getting at. This is kind of interesting because Keith and I have done some other work on how base flow indices changed over time throughout Iowa's major rivers. And, we tend to see this sort of opposite behavior in the major watersheds that we have, where that are overwhelmingly dominated by agricultural land use. So this is just an example of some smooth base flow indices in Iowa's major rivers. And what we've seen over the past century or so is that there's been a pretty consistent increase in many of the sites. A couple of them have leveled out, but you're not really seeing a decrease in any large agricultural basins. This is the one area in Walnut Creek where there does seem to be a bit of a decrease, where because of that prairie, we are seeing lower base flow indices than we saw in the past. We could also tell kind of a similar but somewhat inverse story when it comes to stream flashiness. So stream flashiness is a measure of the dynamics of stream flow. It's a way of quantifying from day to day how much stream flow actually varies. And as you can see in the bottom plot here, that has consistently declined in many of these agriculturally dominated systems. But if you go to the lower portion of Walnut Creek, we see that it's increased. So we actually have a more flashy condition in the downstream portion of Walnut Creek than we do in the upstream portion. One other thing that we're able to do with stream flow is with these continuous records that's a bit more powerful and a bit more statistically robust than some of the tools we talked about previously. was look at just how stream flow has changed across the full hydrologic distribution. So we use a tool called the modified quantile Kendall plot, which I've got shown here, and just take a minute to explain what's going on with this plot. So what we've actually done is conducted a trend analysis on every single empirical percentile of the stream flow records. And so just using a point like this as an example, this would be the median. This refers to the median stream flow at the upstream monitoring site. The way we can come up with this is for each one of the 30 years that we analyze, we take the median stream flow in each calendar year, and then we run a trend analysis on that. The trend analysis then gives us this normalized slope, so this percent per year. So this is telling us that over this 30-year period, the median stream flow at that upstream monitoring site increased by about 1%. So really not that much of a change. We've also color-coded these by statistical significance. You can see that there wasn't any statistically significant trend associated with that value. But what's really interesting is when you repeat this process and you do it for both the upstream and the downstream portion and all parts of the distribution, you see some interesting differences between what's happening at the upstream end, what's happening at the downstream end. And so perhaps most notably, you get this large period here from like the 20th to about the 80th percentile, where the slope is consistently lower at the downstream end. So basically what this is telling us is that for most hydrologic conditions, we're seeing a decrease in stream flow. It's not necessarily just happening during drought conditions, during flood conditions, during mid-range flows. We're seeing this sort of decrease across the board. And it's also especially prominent at the very low end here. So the low flows are lower now at the bottom part of Walnut Creek than they used to be in the past. And same thing is true for the higher flows, so the higher end of the spectrum. And this is the one area where we did get statistically significant values. So we're most certain that the highest part, the wet weather related events, have decreased within the bottom part of Walnut Creek based on this analysis. So just to sum up, we can take a couple of these things together and kind of put our heads together and try to figure out what's probably driving this from a prairie, from a tallgrass perspective, how these things influenced water. So I think what's most obvious is that when you have this tallgrass prairie, it's enhanced the infiltration and the evapotranspiration. So that's what's led to the lower stream flow yields that we've seen in the bottom part of Walnut Creek. We also think that this prairie has boosted the evapotranspiration, and because of that, it's influenced, or it's led to the soils becoming drier and thus leading to less groundwater moving through the system. So we think this sort of lagged approach where it's taking up some of the water and preventing what water would be otherwise diverting rather quickly into the stream. That doesn't happen quite as much. And so that's probably what's behind the lower base flow indices that we're seeing. And then lastly, I think that there's probably some peak runoff reduction that we're getting from these drier antecedent moisture conditions as well. You know, we've all heard in talks about Iowa back in the day in these prairie landscapes that water was a bit more distributed upstream. It wasn't funneled into the rivers and streams as quickly. And so we think there's not as much runoff during these wet weather events, and that's what's leading to the statistically significant decreases that we noted during wet weather events. So just shifting over to nitrate now, you can do a similar sort of analysis, but here, of course, we're bringing in the yields, the flow-weighted concentrations, and the mean concentrations that I talked about before. So I've got these summarized on the slides here. So there's a bit going on. I'll just go through these one by one. The main thing that I want to highlight here is that anytime you're dealing with these water quality parameters, they can jump around and vary tremendously from year to year. So the main factor that's driving at a watershed scale how much of a certain parameter you're seeing in a given year is just the timing and the magnitude of the rainfall that happened. So much of this variable behavior makes these trends a little bit tricky to analyze unless you've got these long-term data sets. What's really important though, is we're looking through these slopes, is to note that again, there's like a hierarchy that exists between the upstream monitoring site, the downstream monitoring site, and the lower part of the basin itself. We find with each one of these parameters that slopes get more negative. So you see steeper declines as you go through this hierarchy, and the slopes tend to become more statistically significant. So you can look at this and really no matter which of these three parameters you choose, whether it's yields, flow-weighted concentrations, or mean concentrations, they're all kind of telling a similar story. But the one other thing I want to note is that you can get some interesting things that pop up here too that are somewhat or potentially unexpected. And if you look at nitrate, this is a good example. So we actually saw a statistically significant decrease in mean nitrate concentrations. And so that can be due to a variety of things. This was the mean nitrate above the prairie. So many different things can influence water quality. Land use change is just one of them. There could be other things going on above stream, but we were only really able to highlight and be confident the fact that the Neal Smith Wildlife Refuge was making a difference when we had these two comparison points. So the monitoring upstream and the monitoring downstream, we saw that despite there being a decrease in the upstream part of the watershed, that decrease was even more pronounced and more statistically significant in the downstream part. One thing that Keith had done a lot of work on throughout the years, and it's kind of circling back, many different instances within Walnut Creek, they've done monitoring at the plot scale and looked at what's happened immediately following the restoration to prairie from traditional cropland. And when you do that, this is an example of one site just showing nitrate concentrations that were collected throughout a given year. If you convert a specific parcel of land from cropland back into prairie, you can see a pretty precipitous drop off in nitrate. So in this one site, values for many years were hanging out around 10 to 12 milligrams per liter. A few years after the prairie restoration, they had pretty consistently dropped down to 2 milligrams. Nothing like this ever happens at the watershed scale, though. Any declines that we see are much more gradual and much more prone to those annual fluctuations in weather that I had talked about previously. So just want to bring that back. It can be very easy to see this sort of thing at the plot scale, but it's very difficult and much more nuanced because so much more is going on at the entirety of the watershed. You can do a similar sort of exercise where we look at the percentage of nitrate coming from that lower basin. You do this, you get a very clear decreasing monotonic trend. So we can be very confident that the Neal Smith Wildlife Refuge has in fact lowered nitrate concentrations within Walnut Creek over the past 30 years. There's a couple of similar ideas about why this is going on, why this has happened. I think perhaps the biggest factor here is just the fact that when you don't have conventional cropland, you get rid of a lot of those traditional nitrogen inputs. And so there's not any artificial fertilizer being applied to the prairie, no synthetic fertilizer, no manure, no fixation from soybeans or other sort of legumes. And so you've got rid of that source. That's probably one of the biggest factors driving this nitrate decline. The other thing that you have now in this tallgrass prairie is just an abundance of perennial vegetation. And so with conventional cropland, you're only getting the uptake from that vegetation throughout about half of the year or so until things are harvested. But with this perennial vegetation, you're getting increased uptake throughout the entirety of the year. So even in the winter, you're having vegetation on the ground. You're always guaranteed to have a cover crop with grassland vegetation, right? So this is probably taking up some nitrate throughout portions of the winter that we wouldn't have with conventional cropland. And then lastly, what's happened here, and this is probably driving some of those gradual decreases, is that there's just a high variability in the groundwater travel times that we have in this basin. Sometimes groundwater only takes a year or two to get from a specific plot to the downstream portion of the watershed, but in other locations it could be much longer and even spanning many decades. So because of that, and because these prairie installations didn't take place all at once and didn't take place at necessarily any sort of structured approach throughout Walnut Creek, we think that the differences in locations and these variable travel times kind of contributed to this more gradual, smooth decline, and thus we haven't really seen any big drop-offs that we can identify at the plot scale. And so lastly, we just want to talk about sediment, do a similar sort of breakdown to what we had with nitrate before. Again, here we're seeing that same sort of hierarchy for each one of these parameters, where the slopes, whether you're looking at yields, whether you're looking at flow-weighted concentrations, or whether you're looking at mean concentrations, they're always steeper as you look at that lower part of the basin, and they're always more statistically significant. Sediment is a little bit trickier than nitrate. The story is probably not as clear and not as evident as the statistically significant declines that we were seeing with nitrate. One of the things that complicates sediment is that it's really highly tied to erosion that's driven by wet weather events. So some of these values jump around tremendously from year to year. You can get quite a difference in flow-weighted sediment concentrations from one year to the next. And so there's just a lot of inherent volatility. But the other thing that's perhaps more nuanced here that Keith has done a lot of work with in the past is just trying to identify where the sediment is actually coming from. And so There was some work done, I guess about 15, 20 years ago or so, going back to that paired watershed monitoring approach that Keith described, trying to determine how much sediment reduction we would see within Walnut Creek, where we had this big land use change conversion to Squaw Creek, which was that northern watershed, which basically none of the land use changed. And in fact, they actually saw an increase in row crop acreage over 15 years. When you plug this land use information into the universal soil loss equation, it projected a big decrease at Walnut Creek and a slight increase at Squaw Creek. So everybody thought, okay, this is going to lead to significant amounts of erosion control, specifically sheet and rill erosion. But then when people actually went out and measured the data collected at both of these watersheds, we effectively saw no significant changes in the erosion that was taking place. And so this really led people, and along with some other field work that was conducted, led people to conclude that stream bank erosion was the dominant sediment delivery mechanism within the lower basin, within Walnut Creek as a whole. And so you're not seeing as big of an effect of the prairie as you might expect, because that prairie is largely going to control sheet and rill erosion, whereas the stream bank erosion is probably going to be less effective. So you put this all together, you run a similar sort of analysis here for suspended sediment. What we get is what looks to be a monotonic trend, but it's not statistically significant. Things can jump around from year to year. We get a p-value here of 0.3, so that doesn't really pass any statistically significant threshold, but it seems like we have declines in sediment, but again, it's not quite as straightforward as it is for stream flow or nitrate. So just to summarize what we think is going on here, there's no reason to believe that stream bank erosion would not be the dominant contributor over these more recent 20 or so years. So we think it's still the factor that's playing the biggest part. What might have happened, though, is that with some of the runoff declines that we've mentioned, specifically during these peak flow events, stream power is probably decreased because of that. When you have lower flow, you have less stream power, less velocities. So that may have resulted in less erosion. So you're actually getting sort of this indirect benefit from the prairie where it decreases the flow rates, and that's what's decreasing some of this erosion via the lessening of stream power. And then finally, there is good reason to believe that there is some on-site soil retention happening. So there is some decrease in sheet and rill erosion, but just with the work that's previously been done in this incised stream environment to highlight how big of an impact stream bank erosion has, we think this is minimal. This is not the major factor driving what's going on. So in order to bring everything together to conclude all these findings that we've talked about, I do want to point out that we think this is essentially, again, one of the rare examples where you can denote what has happened, where you can denote statistically significant changes in water quality that are primarily resulted from land use. So Walnut Creek has been a great example of that. However, you got to recognize that this is sort of a best case scenario for a couple of different reasons, and cover these in the major lessons that we've learned throughout this 30-year project. But first and foremost, you just don't have many watersheds where land use has changed this dramatically. Certainly not anything like going from cropland back to grassland or native prairie. But equally important to that, having this big amount of land use, is the fact that we had these 30 years of data. So because of the variations that you can get in water quality from year to year, it is absolutely essential to have multi-decadal monitoring to detect these changes at the watershed scale. Just as important, though, was bringing in this paired watershed approach. So because so many different things can influence what happens with water quality, land usage is one of them. Things like climate, things like changing agricultural practices, different economic drivers, things that control the source of nutrients or sediment going into a watershed, they all have a part to play. The paired watershed is the best thing. The paired watershed approach is the best thing that you can do to try to denote or to try to remove the influence of those external factors. If you have two watersheds where just one of those things has changed, in this case, land use, this provides the best tool for trying to identify what that one specific factor has done to downstream water quality. And then finally, one other big lesson from this is that while if we were to run this sort of experiment again in a different part of Iowa, you can make some general conclusions. We can say that this sort of conversion is very, very likely to increase or to improve water quality downstream, but it's incredibly difficult to be prescriptive about how much that's actually going to happen without site-specific modeling. So again, so many different factors control how much water quality, or what the actual water quality levels are going to be at any given time. And just to put it another way, if we had flipped in this watershed where the Neal Smith Wildlife Refuge was, and it was in the upstream basin instead of the downstream portion of the basin, we would expect these same general trends to hold. But we're not going to, if that were the case, we're not going to see the exact same slopes that were reported. We're probably not going to get the same exact levels of statistical significance. The timing of when the prairie was produced, the amount of weather that we had going in from year to year, those all play a part, and that sort of thing for any future project will make any sort of these prescriptive recommendations more difficult. So you can't just run this again at a different watershed and say, oh yeah, we expect a reduction of nitrate of about 0.5 milligrams per liter per year. It's more complicated than that and influenced by a whole host of local factors. And so everything that we've talked about today is highlighted in this paper that was recently published with some of our colleagues over at the ARS. There's been a really, really rich literature of scientific data that's been produced and papers that have been published over many different projects that have happened within the Walnut Creek. And so people are interested in, you can dive into a couple of papers that have talked about these sort of things that we've discussed today in greater length. So before we take questions and turn things back over to Matt, I do just want to mention a couple of acknowledgements. So first and foremost, the Iowa Nutrient Research Center, which was our funding partner in this project. Keith and I were talking before this, and you've seen how we've done these sorts of projects for a couple of years. It's often the case that we have these great data sets and we have agencies that are going out and collecting them. But often, a lot of times, they don't really have the scope or the bandwidth to be able to go and interpret that data and nest their findings within the larger scientific literature. And so the Iowa Nutrient Research Center really allowed us to do that and allowed us to make this work happen. So a big thank you to them. And I'd also like to thank our colleagues over at the National Laboratory for Agriculture and the Environment. So particularly Kevin Cole and Ken Waka. They were instrumental in collecting a lot of this data and helping us out with its interpretation. So Walnut Creek is just a small piece of the puzzle that the National Laboratory for Agriculture and the Environment is working on. So we really appreciate all of their work. And then lastly, I'd just like to thank everyone that's been involved with the Neal Smith National Wildlife Refuge throughout the years, including the staff there and including all of the people that have led a lot of the great fieldwork campaigns that have happened. It's been a tremendous resource for us in Iowa that's produced a lot of great public outreach and a lot of great scientific literature. And we've been very fortunate to have them as a partner through all these many years. So with that, I will turn it back over to Matt, who I think has a few administrative slides to go through before we take questions.
That's right. Couple logistical slides. You guys can catch your breath. We got some great questions in already, but get them in if you have additional ones. Let's go to the next slide, Elliot. And okay, just want to acknowledge these conservation webinars would not be possible without the great partners with Iowa Learning Farms, Iowa Department of Agriculture and Land Stewardship, Iowa DNR, the Iowa Nutrient Research Center, and the Leopold Center for Sustainable Agriculture. So thank you so much for your support of the Iowa Learning Farms and in particular these conservation webinars. Let's go to the next slide, which should be, if you watch this webinar live and are wanting to earn a CCA CEU, you need to email Elena Whitaker, ALENAW, at iastate.edu by 5 o'clock today, including your name, the name you entered to watch the webinar, and your CCA number. Again, ALENAW at iastate.edu. Okay, next slide, which is likely the voluntary demographics survey. If you watch this webinar live and are willing to fill out a voluntary survey, that would be greatly appreciated. You can scan that QR code or go to the link there. Only one survey response is needed for all 2026 webinars. So if you've done so this year, thanks very much. And if you're willing to, we'd appreciate that as well. Let's go to the next slide, which should be, we're still on perennials next week. So Jessica Gutnick, associate professor at University of Minnesota, I probably did very poor on that last name, is going to talk to us about perennial small grains, Kerns as a model for crop development and ecosystem service improvement. So please tune in next week for that. I think that has all of those. Okay. Keith and Elliot, we got some questions in here for you. First one, what percent of the watershed has been converted to prairie?
Well, I've got it on that slide.
Okay.
Is it
What's
okay if
that
I go
number again?
back through
Yeah.
it? So this is it right
Okay.
here. So overall, it's at about 30%
Okay.
now. And then in that lower portion of the basin, it's about 45%.
Okay. And that didn't happen all at once. That kind of happened over time, didn't it?
Correct. You can speak a
Yeah.
little more to this, but
Yeah.
most of it happened in the first 10 years following 1990.
Right. It was a lot from 95 to 2005, and it's slowed up considerably the last 10 or 15 years.
Yeah.
And
How
I
maybe
guess we should
oh,
mention too, there's a tiny bit of oak savanna that exists
oh yeah,
within
that's right. Yep.
the Neal Smith Wildlife Refuge, but that was all mostly maintained, and they weren't actively installing new oak savanna. The
Yeah.
restoration pretty much specifically focused on the prairie.
Yeah. Um, this is I think Keith has done a little work on this. Do you have any estimate of the mean travel time of groundwater in the Walnut Creek watershed?
Yeah, we've done it a couple different ways, from GIS-based model to ModFlow. It ends up being about 10 years.
Okay.
So, and that includes probably 100 years from an upland, a long ways from the valley, to less than a year in the riparian zone. So
Okay.
an average of 10 years.
Okay. And maybe this might have been on there, but what would you estimate the overall nitrate reduction in the area from 1995 to now, kind of over that 30 years?
Well, let me go
Yeah.
back to that slide again.
Yeah.
Bear with me as I'm scrolling through here. So this is the nitrate. So it depends on what metric you're looking at, right?
Okay.
Are you looking at load? Are you looking at concentration? But
Yeah.
this is the sort of slopes that we tend to see here. So I'll just focus on the lower basin here. So
Yeah.
it's about 0.37 decline in the yield from the lower basin per year. And then a 0.13 decline in the flow weighted concentration.
Okay.
Again, this is per each one of the
Yeah.
years.
So over 30, so on that flow weighted concentration, 0.13. So over 30 years, about 4 milligram per liter reduction. Is that about right?
Yeah,
think?
so
Yeah.
30 times this would get
Yeah.
you at
Yep. 38 times. Okay. Great. Second, sorry. Oh, somebody asked, something special seems to be happening around 2006 to 2007 in the nitrate percentage yield. Have you also detected that, and could it correspond to something happening on the land?
So I
Oh,
imagine they're talking about
yeah,
this handful of
high
years.
flow.
Yeah, I think that's just a weather-based
Yeah.
phenomenon more than anything else, right? So I'd have to go
I,
back and
I,
check the records for
Yeah, it
sure.
was, so I was there. So 05 was really dry, and
yep.
then we just instantly got wet. You know, if you remember, like
I,
07, 08, and you
I,
could really see it in the sediment peak.
Mhm.
It was really wet.
yeah, I can attest to that because oh, '08 was the year that we got the pictures from the flumes because we had like a 4-inch rain in June
Yeah.
of 2008. And also, one thing to note is that one in, I think, 2010, you saw that big nitrate yield. That was the year that in August of that year was about 10 or 12 inches over about a week period down there.
One other thing I'll mention, just since we're on this topic, there was one year on the opposite end of the spectrum. Look at what happened in 2023. We actually have a negative flow weighted concentration. And so that was a drought year. And so the lower portion of the basin actually became a nitrate sink. So less nitrate
Oh,
left it that went into it.
okay.
So you can get, again, the weather varies a lot. You can get all sorts of behavior. And we did throughout this 30
Yeah, which again argues for the 30-year record.
30,
'Cause
yeah.
otherwise, you start and end this monitoring period at different times, you're gonna get very different results. So
Yeah.
if you take like a 3-year or 5-year window, you could have increases, you could have decreases.
Yeah.
This 30 years allows you to know what the overall trend is.
Yeah, I look at, like your annual concentration graph. If you were just monitoring from like 2012 through 2015, you'd say the nitrate concentration's going up, right?
Yeah,
So,
exactly. And
yeah.
so starting and ending is just very important, and that's why that long record is needed.
Yeah. here's one. Somebody had to get off, but they had a question for you because they said they were going to come back and watch the end. So, well, do you know if this Walnut Creek, because there's another Walnut Creek heavily monitored in Iowa, but this Walnut Creek will be included in sampling with ARS as part of the new SEEP Watersheds Legacy P in-stream assessment project?
Unknown, but
Okay.
likely.
Okay.
Likely.
Great. Okay.
They're
Um,
certainly going to continue their monitoring efforts
Yeah.
there for the foreseeable future.
But what we've learned from ARS is they probably will not, they'll do the remote monitoring, probably not invest as much time and effort on all the grab sampling they've done.
Okay.
So there will be some continuing, but it will not be to the same degree as it has been.
Yeah. And I guess I should say this, at least as of right now, ARS has continuous nitrate sensors at your WNT1 and WNT2, if I'm not mistaken.
Correct. Yes.
Yeah. Okay. Um, did you break out N loads per unit of cropland in the lower watershed to see if the prairie was intercepting cropland loads or if the load reductions were just due to land conversion?
So we didn't, with the monitoring that was conducted here, we didn't quite have the ability to do that at the watershed scale, because everything that we were focusing on now, or everything that we we're focusing on with this study was kind of centered around those two particular spots. I think what this question is getting at, though, is could you actually go in and try to divvy up a little bit more in that lower basin, what the prairie contribution was, and what the area was that remained in conventional cropland, because there was a bit of that in the lower basin. So you could do that, but I think you'd have to bring in some more geospatially explicit modeling beyond what we've done here.
Mhm. This is a good one. Do you think these trends will continue to kind of decline, or do you think the system maybe near a new equilibrium?
We think they'll continue to decline.
Okay.
There is going to be a point of diminishing returns though. That's we don't expect it to go all the way down to zero and bottom out there, because of course you still are going to get some influence from the areas that are in conventional cropland. But I believe it'll asymptote out over the upcoming decades here. But when that's actually going to occur and how long, we're not totally certain. As Keith had mentioned before, the variable groundwater time introduces a bit of uncertainty to when we're actually going to see all of the full benefits of this land use restoration.
Okay. This one, I think, kind of for Keith, and at least just to kind of bring it up because you probably know who would be the lead author on some of these things, because somebody's asked if there have been any soil samples collected and analyzed for soil health to look at how the prairie might be impacting aggregate stability or infiltration rate, which could lead to more base flow and less flashiness.
Yeah, we are currently investigating the changes in soil carbon, and
Okay.
we'll have an interesting story to tell there. Elliot, again, has done outstanding work looking at the cabbage site, the small catchment, and we've got, again, a 20-year plus record of soil carbon changes there. So we're seeing that, and it's a very interesting story. All the aggregate stuff, not that we've ever done. I think Mahdi Al-Casey was out there, and he did some of that. So it's been a little bit of hit or miss out there. And if somebody has a lot of interest, I think it'd be a great thing to investigate. But
Yeah, I think Cold Dutter might have done a little bit of that on some of our prairie strip sites there,
yeah,
but I
it's
just can't.
less
I
comprehensive than what
yeah.
this is. Yeah.
Than this. Yeah. Okay. Um, here, oh, let me see here. Just trying to get through some of these. I guess, was there any monitoring at WNT1 and 2 before the prairie restoration began?
No, it was very, very limited. There,
Yeah.
handful of grab samples for a couple years before that. So, you
Yeah.
know,
Yeah. Okay. has the age of the riparian stream banks been studied? The steep banks suggest deposition from upstream erosion during early agriculture.
Yeah, we definitely see accumulations of post-sediment alluvium, which is that material that was deposited and eroded from the uplands and deposited in the near stream. Ranges from like 3 to 5 feet thick through that entire section. So there's a some element of the bank erosion is simply sediment that was eroded from the uplands that are now in the stream corridor. Interesting, if you go back in the history of Walnut and Squaw, the other paired watershed, they were already noting, if you look at old survey reports, by steeply incised banks, like in 1910. There's an early report from, you look at the geology of Jasper County, and there's a picture of Squaw Creek with like 20-foot deep banks.
Wow.
So we haven't, channel incision has been a problem out here for a long time.
Yeah. Here's given the likelihood that the suspended sediment concentrations increase during flow events, how do you think sampling every 2 weeks might have affected the estimates of your suspended sediment loads and patterns?
I really don't think it made much of a difference. So the sampling was conducted almost without kind of agnostic of the hydrologic flow conditions. So it really didn't determine whether or not they were going out and collecting that data or not. So we don't expect it to really be biased in any particular way by the stream flow. And then I'll also say what the model that we used for this, the WRTDSK, that does a good job of trying to account for any of those situations that may have been oversampled or undersampled. And so I think the statistical approach that we chose here kind of accounted for some of those underlying variations that the grab sampling can potentially miss.
Okay. Here's kind of thinking maybe bigger picture is, understanding that these are Walnut Creek watershed specific results. Do you have any inclinations or thoughts from this research as to what the threshold is in terms of percent of the watershed in perennial vegetation to see a watershed scale improvement, or how might you model an estimate of this for different watersheds?
I'll start.
Okay.
We've looked at this over the years in terms of just Iowa watersheds, and I've shared it many times. Like the percent of row crop in a watershed will drive stream nitrate. So if you took the percentage of row crop in a watershed times 0.1, you're roughly at the mean annual concentration.
Okay.
So it's like, if you decrease that row crop and add perennial vegetation, you are going to decrease nitrate by simply like what we saw with Walnut Creek. You're removing the source areas, and now you're getting that perennial signature on the land. So there's a really direct relationship between that, and I think and for sure, the Walnut Creek's data and implications will apply to the landforms that this is in. This is southern Iowa. Old glacial landscape with hills and valleys and so forth. It apply to some level to the Des Moines lobe, but then we have a lot of the tile drainage signature on that as well. So I think it applies very well to the landscape. In general, row crop and perennial are tied very closely in stream nitrate, and this is nothing, it just totally emphasizes that, I think, in even more detail.
The only thing I'll add is just the percentage of land use that you convert. That is going to influence how much monitoring, the length of monitoring that you need to see that sort of change. And so it's definitely possible that you could detect something like 10% land use change over the course of like 50 years. That's the time frame you're going to need for something like that. If you were to ramp that up to something like 80 or 90%, then over the 10 years, I'm almost certain you're gonna get that sort of change. And so those two things are very much intertwined and interconnected.
All right. Well, I think that we probably better stop there in the interest of time to let Elliot and Keith get back to their regular scheduled programming. I just want to thank you both so much for the presentation today and for this work. It's super important for for Keith and everybody that was involved from the start. Somebody that was on here said they met you, they remember visiting with you at the initial project tour in 1995 as part of an EPA National NPS conference in
Yeah,
Miami. So,
wow.
it's great that it's uh, been able to go on this long. So, thank you both. If somebody needs a CCA CEU credit, email Elena Whitaker, ALENAW at iastate.edu. Email her by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. And I want to put a shout out again. Please tune in next week for hearing about Kernza. So, all right, everybody have a great day.